Okay, so mesh analysis uses voltages, whereas the node voltage analysis uses currents. And what you do is you draw loops around each mesh, and if you want to keep your life simple, you'll make your loops all go in the same direction. There's no rule, but it really will help you. And so I usually make my loops go clockwise, but not always. It just depends. And my rules are, entering a voltage source in negative side gives a negative voltage. And if we have a resistor that's shared, so let's say I have a resistor that's shared, and I have I1 here and I2 here. Well, hold on, before I do that, let me just say that I've got a resistor that's not shared, and I've got I1 going that way. Then when I add that up, that's voltage is just going to be I1 times R. But when I get to a resistor that's shared, that's going to be R times I1 minus I2. Because if I'm working on my I1 loop. So this is from my I1 loop, because my I1 will be positive and my I2 will be going in the opposite direction of I1. And you'll see how that works. It'll make more sense in a minute. So I'm going to call this one I1 and this one I2. And I'll start going into this negative 12 volt voltage source. So negative 12 volts, and then plus I1 times 4, and then plus 3, and that one's shared, so I'm going to say I1 minus I2 plus 2I1 equals 0. And that's my equation for the first mesh there. So that's negative 12 plus 4I1 plus 3I1 minus 3I2 plus 2I1 equals 0. Or 9I1 minus 3I2 equals 12. And then I can divide everything here by 3. 3I1 minus I2 equals 4. Now I'll do the second mesh, and I'll start right here at the shared resistor. So I'll say 3 times I2 minus I1. This time it's I2 because I'm in the I2 loop, plus I2 times 5 minus 4 equals 0, or 3I2 minus 3I1 plus 5I2 minus 4 equals 0, or minus 3I1 plus 8I2 equals 4. Okay, so now I have these two equations. I'm going to pull this one over here. And I was about to get out the calculator until I see how easy they are to solve. I2 equals 8. I2 equals 8/7. Yeah, and then it's not. Then I have yucky numbers, which is 1.14 and 3I1 minus 1.14 equals 4, and I may or may not get that I1 equals 1.71. That's what I got. Okay, now let's go back and see what it was looking for. So it was looking for I, and the way we have it drawn, we need to be careful because I is not just I1. I is I1 minus I2. And so I is going to equal 1.41 minus 1.71. Which is negative 0.3. Now if I were interested in I through the 4 ohm resistor, that would just be I1. But going down here, that's a combination of I1 and I2. Okay, so are there questions on this one? Okay, so I am unfortunately out of time. She did tell me that y'all might have some questions like the ones from chapter 1 on current and charge. And I think I do have one of those. Would y'all like to look at that in the last few minutes? Or
Yes, that would help.
okay. I don't know what problem this was. Okay. All right. So the cumulative charge in millicoulombs that entered a certain device is given by this. And I wonder what the question is. The question is plot Q of t from t equals 0 to t equals 60 seconds and plot corresponding current I of t entering the device. Okay, so Q of t in millicoulombs and time in seconds. So we know it's 6, it starts at 0. And then it's 5t for t between 0 and 10 seconds. And the thing to remember is if something is linear, you only have to have 2 points to draw the line. And 5t is certainly linear. And so at 10 seconds, our millicoulombs are 5 times 10 are 50. So I'll put that up here. I'll say that's 50 millicoulombs. And that's at 10 seconds. And I know that's a line. And I'm going to pretend. There we go. It's a nice dot. Okay, and then it's 60 minus t for 10 seconds for t between 10 and 60. So at 10, if I plug 10 in here, I get 50, which is good because my charge does need to be continuous. And if I plug 60 in here, I get 0. So my charge should go like that. So that would be my graph of current versus time. Now for getting, I'm sorry, charge versus time. Now we want current versus time. And if you don't know it, you should definitely have written on your formula sheet that I equals dq dt. That is important. I is dq dt. So this is I, and it's going to be in milliamps because our charge was in millicoulombs. This is t in seconds. I should have marked that up here. So we'll have our same time scale. And if you remember from calculus, a derivative is just a slope. And if we have a straight line, it's easy to determine the slope. The slope is just the rise over the run. And I do this often. I need a negative for my current. The slope is the rise over the run. And so if we look at this first part, we have our starting point is 0, 0. Our ending point is for this first segment is 10, 50. So our slope is 50 minus 0 over 10 minus 0, or 5. And it's a constant slope at that time. And it's positive. That's supposed to be a horizontal line. We can live with it. Okay, and then for this second part of my line, I have my starting point is 1050, and my ending point is 60, 0. So my slope is 0 minus 50 over 60 minus 10, which is negative 50 over 50, which is negative 1. And that's constant because a straight line has a constant derivative. And they do like to draw these vertical lines. So there we go. All right, so any questions on that? If not, I'm going to have to go. I wish you the best of luck. And like I said at the beginning, if you have questions while you're studying, feel free to answer, but don't expect an answer back until early tomorrow morning because I'm just jam-packed for the rest of the day. But good luck. I hope, was this at all helpful?
Yeah, that was very helpful.
Okay, good. Okay. All right. Well, good luck. Let me know how it goes. Thank you so much for coming.
Thank you.
Okay, bye-bye.